Welcome to the Consulting Specifying Engineer webcast, How to Future-Proof HVAC Systems to Meet Efficiency and Carbon Emission Goals, sponsored by Danfoss. I'm your moderator, Amara Rozgus, and I'm happy to join you today on behalf of Consulting Specifying Engineer and CFE Media and Technology. Here are some tips and tricks to get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast platform. If you are having technical problems with audio or the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks. If you do need a technician, type a message in the Ask a Question box and the tech team will get to you as quickly as possible. Individual user experience questions will be answered in the Answered Questions box. Type questions for the presenters in the Ask a Question box on the left side of your screen. The live Q&A will start in about 45 minutes. And today's webcast is being recorded. You'll receive an email within a week to a link to the on-demand event. To download a certificate of completion and a PDF copy of this presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of this webcast. Here's some info about today's subject matter experts, Drew Turner, John Sheff, and Ken Koehler. Drew Turner is currently Global Marketing Manager for Danfoss Oil-Free Solutions. He's been in the HVAC industry for 23 years and with Danfoss for the last 6, holding a variety of roles over his career, including product support, product marketing, product planning, strategic planning, and business development and market research. He holds a bachelor's in industrial engineering from Oklahoma State and an MBA from the University of Colorado. John Sheff is currently the Director of Public and Industry Affairs at Danfoss, where he covers a range of issues, including refrigerants, energy efficiency, electric vehicles, and urban development. Previously, he worked on energy, climate, and sustainability policy in the office of Maryland Governor Martin O'Malley before earning an MBA from the Robert H. Smith School of Business at the University of Maryland, College Park. Ken Koehler serves as Senior Business Development Manager for Danfoss Cooling. He's responsible for key global customers and growth of new customers. Ken has been with Danfoss for 14 years, focusing on oil-free compressors with more than 30 years of experience in HVAC and aerospace defense, including sales, project management, quality, and sustainable engineering. Ken has a BSIE from Southern Illinois University and a master's in system management from Florida Institute of Technology. Thanks for joining us today, gentlemen. Let's begin. John?
Thanks, Amara. Again, my name is John Sheff. I'm the Director of Public and Industry Affairs at Danfoss. And today I'm going to give a brief overview of climate policy in the United States. Climate policy in the U.S. is currently fragmented. There's not much federal leadership, and that means that nearly half the states have joined the U.S. Climate Alliance and have developed their own climate policies. Some of these states have set very ambitious goals, including California and New York, which we'll get to in a moment. And perhaps most consequential, several major cities have passed the most significant building emissions laws we've ever seen. In the past several years, for better or for worse, the federal government has pulled back from further regulating climate. The Trump administration officially withdrew from the Paris Climate Accord and has showed little interest in bringing the Kigali Amendment, which regulates high global warming potential refrigerants, to the Senate floor for ratification. Meanwhile, as younger generations mature politically, they're pushing politicians to engage more on this issue and make it an election year issue as well. And last year we saw climate protests in many major cities around the country. The U.S. Climate Alliance is a group of governors who have committed their states to upholding their commitments under the Paris Climate Accord. This alliance now includes 25 governors, covers 55% of the U.S. population, and includes an $11.7 trillion economy. New York and California are both Climate Alliance members and have set some of the most ambitious goals in the country. California is committed to lowering its emissions by 40% below a 1990 baseline, while New York is going even further, aiming for 85% reduction below that baseline by 2050. It is cities, however, that have made the biggest impact with climate legislation. In 2019, New York and Washington, D.C. both passed building emissions laws with real financial teeth. These laws have the potential to spur the retrofit market in commercial buildings in ways we really have not seen before. In addition, around 30 California cities have passed legislation or ordinances that ban natural gas infrastructure in new construction. And other cities in places like New Jersey and Massachusetts are following suit. New York and Washington, D.C. each passed tough building emissions laws meant to sharply reduce the greenhouse gas output from existing buildings. While the two laws have different mechanisms, they both create an emissions cap and put pretty strict penalties in place for building owners who do not comply. In New York, when the first cap goes into effect in 2025, it's estimated that 25% of the city's commercial buildings over 25,000 square feet will need to make some sort of improvements to comply. In 2030, however, when the emissions cap is adjusted, it's estimated that 75% of those buildings will be affected. In Washington, the city is using a median Energy Star score as its cap. That cap, though, periodically adjusts downward as more buildings comply, forcing more and more buildings into the program. And while DC has yet to lay out exactly what the financial penalties will be, they are expected to be substantial. While building emissions laws that target retrofits are emerging in large cities on the East Coast, electrification policies focused on new construction are popping up in small and mid-sized cities on the West Coast and spreading to the rest of the country. I put this quote from Colorado's energy director at the top of this slide to illustrate the enthusiasm in certain places for these types of policies. More than 30 cities in California alone have passed some sort of natural gas ban, and the state is now being forced to address the patchwork of regulations that's emerging. And in some places like Arizona, we're even seeing a backlash in the form of preemptive state laws prohibiting cities from banning natural gas. And now I'm going to pass it over to Drew Turner, who will go through some of the consequences of these different policies. Drew?
Thanks, John. Yeah, so now I'm going to talk about the major factors that are related to the trend to, or the drive to future-proof HVAC systems. And what you see here is just highlighting the future-proofed HVAC systems in the center. But the major driver for that is, of course, and what we see happening today, which is really changing the definition and the list of factors which drive a future-proofed HVAC system, with the ultimate goal of decarbonization of those of the power sector. And the major factors that come into play include one that's been around, ever since HVAC systems have been around, which is efficient. They need to be efficient. But more recently, you've also seen that they need to be electric. And specifically, what's changing today is the electrification of heating and the move to heat pumps. And then they need to be resilient. And so that word is kind of a transition of the reliability word, whereas it was mainly focused on reliability in the past, It focuses on resiliency today and anticipated to be in the future as well. And I'll talk about the HVAC component factors that tie to each one of these as well. But they also need to be grid interactive. That's a new one, and I'll talk about the HVAC components that tie into that as well. So the HVAC solution component factors, which really tie into these, some of these are no change from what's been critical in the past, and some of them are relatively new, and some of them have evolved to include other factors as well. But what you see on the top left-hand side in terms of tied to efficiency is, of course, variable speed. That's been around for a long time. It's just becoming more critical today, whereas, basically drives are, starters are really placeholders for drives. You see that becoming more the case today, and drives being really a ubiquitous expectation for HVAC systems. More recently, we've seen the recognition, and this ties to another HVAC system factor down below, but I'll get to that in a minute. But performance over time becoming more critical. As HVAC systems become more connected and more tracking of performance of equipment is done as a result of that connectivity, the realization of performance over time becomes much more critical, and maintaining that performance over time becomes much more critical. As I mentioned before, the electrification and specifically the electrification of heating is becoming a major factor. And the major factor for HVAC systems related to that is the trend to heat pumps, both air-to-water heat pumps and water-to-water heat pumps. In the past, as I mentioned, resiliency was really defined as reliability, and especially for mission-critical type systems. What has really become much more critical or added to that factor more recently is the coupling of those systems and the symbiosis of them, basically moving heat from where it's not needed to where it is needed, and the tying in of HVAC systems across buildings for more of a microthermal grid in addition to the microgrid trend that you see from the power side. So tying those two in together, and then of course related to that is the connectivity. So if you're going to have a more resilient system that ties in together the systems of multiple buildings for a microthermal grid system, then it's very critical that all of those components and systems are connected, and that you understand both the real-time operating cost and the operation of each one of those components in the systems. Tied to that grid interactive factor as well is the demand limiting. So grid interactive efficient buildings, number one factor that comes into play for HVAC systems is the ability to respond to the utility signal to demand limit those components. That in turn also of course ties to variable speed and the ability of a variable speed HVAC system to exactly respond to that demand limiting signal and closely match the thermal load at the same time. So now I'm going to dig a little bit into the heat pump factor. So what we see, the number one factor that we see changing with HVAC systems in the future, as opposed to what we've seen in the past to drive a future-proofed HVAC system, is the change from fossil fuel source heating to electric heating, and specifically with the move to heat pumps. And that's really driven based on the fact that fossil fuel source heating is inefficient, with a COP of approximately 1, and it also drives the emissions of CO2 and other gases which are harmful to the environment. As opposed to that, and this is even accounting for the generation and transmission losses associated with utility-driven electricity, this is a much more efficient system. So about 3.5 times at the end point, but even accounting for those losses, it's a significantly more efficient system. And based on the modeling that we've done, and this is just a conservative estimate for one application, but around driving an opportunity for around a 35% operating cost reduction and 60% emissions reduction opportunity. And Ken's going to speak to the specific solutions which will allow those numbers as well. But what I spoke to on the previous slide was a baseline where all of the electric utility power is driven by fossil fuel sources at the electric utility source itself. What the decarbonization drives, though, is the drive to decarbonization drives is a reduction in the energy consumption, as I mentioned, and the decarbonization of the energy consumed. So if you're using fossil fuel sources for that electric utility and you transition it to renewable energy, that is what drives the ultimate goal of decarbonization. And I'll speak to why that is, why the heat pumps and the electrification is really preparing for the future and the integration of those renewables. But first, I'm going to touch on what's changed in the last few years on this. And this is really critical in the future-proofed HVAC system goal. What you've seen in the last few years is a significant change in the commitments of individual states to integration of renewables into their power grid. So what you see on the right-hand side there is just last year, we had a number of states commit to 100% or in that area renewable energy in the 2030 to 2050 timeframe. That only matters, though, if the reality of what's being implemented reflects the policy of what's being planned. And this shows a snapshot from the EIA of the planned new power generation in 2020. And what it shows is that 76% of the 2020 new U.S. power generation capacity is renewable. And if you know a renewable grid and the other factors that come into play, also driving the grid interactive efficient buildings, you know that that's about at entitlement, because you always have to have some level of what's called peaking plants to address those gaps that you now see with a renewable grid on the supply side. Formerly, you had peaks and valleys mainly driven by the demand side. Now you have them also driven by the supply side. And so you have to have those peaking plants, those natural gas peaking plants shown here, to continue to address those gaps, in addition to the other solutions that you can provide on the demand side, which I'll touch on later as well. So the ultimate goal is emissions reduction, right? And what we've seen is, and all of that only matters if the reality reflects the policy. And what we've seen in the last several years, again, is a significant growth in the use of renewable energy and the integration in the power grid. What that in turn drives is a significant additional reduction in the CO2 emissions from the electrification equipment that you've implemented. So if you remember back on the first slide that I showed, it showed the potential for around a 60% CO2 emissions reduction based on 100% fossil fuel source electric grid. As you integrate in 10%, 20% renewables into that grid, the corresponding CO2 emissions reduction resulting from the implementation of that heat pump as opposed to the fossil fuel source boiler also goes up. Now I'm going to touch on a few of the, what we're seeing with the energy costs and the utility programs as well. What you see is that the utilities are driving the demand side electrification programs. And specifically, they're creating these electrification programs, and several of them just in the last couple of years. You see a significant trend in those electrification programs, including advanced heat pumps and grid interactive efficient buildings, which really ties to it, in the last few years to drive those demand side changes, which also allows them to put off the more capital intensive changes of those fossil fuel source generation to renewables. So you can drive those CO2 emissions reductions of the utilities. The investor owned utilities can drive those CO2 emissions reductions through demand side changes in addition to the supply side changes. And so that's why you see those electrification programs being created also, is to drive that. And what you also see is that, in tying to this, the other major HVAC critical factor that we see, of course, is continuing to drive energy efficiency, including through variable speed, integration into HVAC systems. You also see that the electrification programs really drive the efficiency option. And efficiency itself is always the lowest cost energy source. Said another way, the energy that they don't use by utilizing a more efficient variable speed drive HVAC system is always lower cost than new generation to account for that lower efficiency system. And as the renewable volume goes up on the electricity grid, based on the trend that I was just talking about, so the cost also comes down. And that's what you're seeing, is that the wind and solar on the renewable side are significantly coming down on cost and will continue to come down on cost. But in the meantime, energy efficiency is by far the most efficient or lowest cost generation source. We've also seen a significant change in the number and the content of those electrification programs. So this just shows a snapshot. ACEEE is a great resource for what those electrification programs are, both locally and across the nation. And what you see here is a snapshot from them summarizing some of the electrification programs that have been put in place. They are today centered especially around the Northwest and Northeast, but they're expanding to other localities as well. And we're expecting that that is going to continue to evolve also. The other factor that comes into play, and if you remember back to my first slide, the other factor that really comes into play here is reconnecting the supply and demand. What I was just talking about on peaking plants and how you're at about entitlement with 76% renewable generation planned this year or being implemented this year, you also have to address, in addition to those peaking plants, be able to address that additional disconnect that you create from the supply and demand by integrating in those renewables on the demand side and also on the supply side by integrating in energy storage. Energy storage takes various forms, including batteries, including pumped hydro, including thermal storage. And the major point that we try to get across is that by far the most cost-effective form of energy storage today is thermal storage. And energy storage costs in the form of batteries are going to continue to come down. They're coming down today. They're going to continue to come down, but they're still in the range, thermal storage is still in the range of about 1% to 5% of the applied cost of battery storage. And we expect that that difference is going to continue for a while as well. The other factor that I mentioned earlier is grid interactive efficient buildings. All of this ties together. That's the major point. All of these factors tie together. And this is grid interactive efficient building summary of impact of HVAC system solutions to address the grid interactive building goal. And this comes from the DOE. But what it shows is much of the same factors and solution factors that I talk about for HVAC systems in the previous slides also ties to the grid interactive efficient building goals, such as thermal energy storage and modulating vapor compression. Another factor that comes in here that I'm going to speak about on the next slide is district energy systems, which has been, we just talked to the DOE on this yesterday, but has been significantly missing from these discussions previously. You also see other HVAC solution factors coming in here, such as liquid desiccant thermal energy storage systems. So they take different forms, but they all have that ultimate goal of reconnecting the supply and demand and interconnectivity to drive reaction to variations on the supply side from the utilities. As I mentioned, significantly missing from the conversations thus far on grid interactive efficient buildings and future-proofed HVAC systems has been the potential of district energy systems to address all these goals. And this is one of the things that we've been highlighting, is that a district energy system has built-in redundancy, storage, and resiliency, which is your ultimate goal here. So if you're reconnecting supply and demand based on the integration of renewables, a district energy system, and also incorporating thermal energy storage is a fantastic way to do that because of both the thermal flywheel effect of the district energy system itself, as well as the options that it creates for both recovering heat off of different sources in the system to move them to where they're needed and away from where they're not needed, and then to turn down those those generation sources that are built into this system as needed based on the demand signals or the demand response signals from the utility. What we also have seen is that with district energy systems, and especially district heating systems, there's been a significant evolution in the European solution market for this, and integrating in and planning out the electrification of those district energy systems and the application of heat pumps, and specifically water-to-water heat pumps, as a fantastic solution for both the electrification and the ultimate goal, which is decarbonization. And what this shows is a snapshot of the different energy sources utilized for those water-to-water heat pumps for those district heating systems. It's a tracking of both the operating temperature as well as this percentage of the overall application of those water-to-water heat pumps in those district energy systems. And what you see is there is a very consistent higher volume source of those. But what you've also, when you dig into this and you start to see what's happening in the market today, you see that those more distributed, smaller capacity heat recovery sources are becoming much more prevalent, as opposed to more of the centralized utility-driven generation. So much like the move from a macro grid to a microgrid itself, and a macro thermal grid to a micro thermal grid, with these district energy systems, it's moving out to the outer reaches of those district energy systems. And now Ken is going to touch on the specific solutions that Danfoss has to fit with these trends.
Good afternoon. My name is Ken Koehler. I'm the Senior Business Development Manager for Danfoss, focusing on both variable speed technology, both in oil-based systems and variable speed scrolls, and also our oil-free centrifugal compressors of our Turbocor. So building on what Drew had talked about with the future-proofed HVAC systems, one of the key characteristics that he talked about included was variable speed. And that comes in both variable speed compressors and fans, but I'm going to focus more on the variable speed compressors. Variable speed technology has offered a quantum leap in energy efficiency. We have implemented into our variable speed oil-based inverter schools and oil-based centrifugal compressors the key thing of inverters to provide that variable energy so we can meet the global demands on each building as they're designed. Several of the benefits offered by variable speed is inverter school technology offers air conditioning systems with energy efficiency buildings, reduced energy consumption, and lower overall running cost. Some of the other things you see as you go down that road of the market, you see people are oversizing systems. It offers reduced electricity bills, lower inrush current, and increased comfort and process are some of the key drivers for variable speed. Some of the other additional opportunities of variable speed is you get energy efficient buildings, reduce energy consumption, and lower running cost. Looking at a building profile, most of the buildings today are designed for the peak load where they operate less than 5% of the time. While it's important to meet those max conditions, we must also consider the overall operating conditions of the building. Capacity modulation attenuates the power demand peaks, which also contribute to increasing the grid reliability and quality of the power supplied. Variable speed compressors also match the power input with the cooling capacity. The unit copes with the effectivity with the changes in temperature and runs a partial load, which can also represent a 30% reduction in energy bill every year as compared to a fixed speed or mechanically modulated compressor. Stable temperature control also secures the process in an optimum way, providing better comfort, also means energy efficiency in the buildings. When we look at inrush current, one of the key things is benefits of it. You see the variable speed scroll and turbocores offer a soft start control, which leads to near zero inrush current, which improves energy efficiency rating. Direct online compressors, they draw 5 to 6% times the normal current when the compressor starts up until it's at the running speed is attained. Traditional fixed speed compressors also can make 8 to 12 start-stop cycles. With every start, they draw that same high current, which leads to high power consumption, also a stress on the supply and a stress on mechanical parts. In comparison, the starting amps on a fixed speed compressor is reduced through variable speed by up to 70%. The Danfoss Turbocor compressor offers a lower inrush current of less than 2 amps to starting amp. Soft starting compressors avoid torque surges, which also prevent higher mechanical stresses, which in turn results in lower service costs and in decreased wear. This lower inrush current also helps saving fixed costs charged by utilities, peak concurrent calculations, and reduces main and power backup loads. One of the things in demand response, a lot of things that Drew talked about, is variable speed compressors offer additional benefits by reducing the load on the grid by varying the speed to meet the cooling demand. The challenge today encouraging utilities to offer incentives to offer rewards for variable speed technology and, of course, demand reduction. Look at this chart. We show a power grid of complex of showing a different load versus time, load and temperature over time. As shown in the chart, 60% of the peak load in a building is consumed by the HVAC system. A variable speed compressor offers the match to the demand load of the building, which also increases the overall EER. Variable speed also offers a power savings. With variable speed, you can achieve the highest energy savings where the chiller operates most of the time, which is in that lower 30 to 70 to 80% time of the range. By avoiding oversizing a system, the key benefits include reduced electricity bills, lower inrush current, and increased comfort and processes. By reducing the speed, we also decrease the sound versus the fixed speed on the compressor. Also in the VFD, you offer lower noise levels. For the fixed speed, this is representing more of a scroll compressor, a 12-ton scroll. Looking at that scroll, you can see there's a fixed speed at 35,000 RPM, whereas as a variable speed scroll, as it goes in lower speeds, the overall dB factor can range anywhere 40% less. And in the Turbocor compressor, one of the key benefits, and that is we offer a lot quieter. It's 8 dB quieter than the comparable screw of the same size. Some of the other benefits for the Danfoss Turbocor compressor is better than 40% load efficiency. And also is in size, it's 1/3 the size of a comparable system, and proven performance reduction over the lifetime of the compressor. And I'll talk a little bit more about that in the next slide. One of the things we've done with the Turbocor compressor is we took some compressors that have been in the field over 10 years. We took those compressors off the chiller they were installed on, brought them back to the Danfoss Turbocor factory, measured the same performance to the same standards that we were shipped at previously and 10 years ago, and we saw zero change in performance, degradation in performance. We plan to include this study to include more compressors, but the key thing there is you had consistent performance over time. It's one of the things that Drew talked about that is one of the factors that people will be looking at in the future is looking at do they maintain that same efficiency and that same capacity over time as the system is installed. One of the other things that's going on is what we call smart buildings or digitalization. And digitalization, what we see is the way it changes the way we live, work, and interact. As you know, we have houses we can talk to the system and tell, turn on the lights, turn on the HVAC, lower the temperature, you control it. If you're on vacation, you control it. One of the things that Danfoss is interacting is a called HVAC 4.0, which implies close cooperation between all stakeholders. End users experience better comfort and improved productivity. Builders get a better operational excellence with lower cost and better ROI. Service and maintenance also turns into a fact-based, easily manageable process where they can now do more reactive solutions versus reactive solutions. One of the things that we've been focusing on the Turbocor and the oil-free side is to come up with a means what we call the Turbocor Cloud Services, With Turbocor Cloud Services, one of the things we're doing is we're beta testing that today. It allows a platform for the compressor to provide insight to what your chiller and your compressor performance is over time. We can monitor the compressors from remote. We can also have a portal where we can now go in and we can access the compressor to see what's going on with it, historical data. We have a diagnostic engine which provides more real time if there's something going to wire with it. The system, it can tell us in advance, which would reduce the number of truck trips out to repair the system. Also, one of the future things we're providing is a health report on the compressor. So we'll provide a health report to the owner. It says, how is your compressor performing? How is it going? And we'll provide that on a periodic basis. Another key addition to that would be a remote assistance where we have a Turbocor product expert who can help with you if you have any specific compressor issues or needs. Danfoss offers a wide range of compressors, both from our inverter scrolls, starting as low as 2 tons or 6 kilowatts, up to 26 tons, and increases the range up to 50 tons through our tandems. Running with R410A, and we're expanding it into all lower DWP refrigerants as well. From that size, moving up to the larger size, Danfoss Turbocor compressors offer a range starting at 50 tons up to 200 tons with multiple different refrigerants we offer in those compressors. In addition, we offer a large BTT or BTX compressor, which ranges from 330 to 450 tons per compressor. And all these larger compressors can be added with multiple compressors to a chiller to achieve even larger tonnage based upon the building requirements. What this picture is kind of showing the overall family of the Danfoss variable speed scrolls and Turbocor compressors. So the range we offer is just on what I spoke before, down from the 2-ton range up to the 450-ton range. Wide variety of applications we can apply to for both comfort and process cooling. There's a need for stable and accurate temperature and humidity controls such as hospitals, IT, telecoms, process cooling. Any of those ranges, we see these applications throughout hospitals, museums, anywhere you need comfort cooling or process cooling, these type of compressors can be applied. So in summary, what I like is the inverter screws and inverter compressors. Danfoss offers a pre-qualified inverter compressor and drives designed to work together coupled with our Turbocor compressors, which have built-in inverters. This adds a long list of benefits to both our manufacturers, consulting engineers, and end users in terms of reduced number of components in the system, higher reliability and continuous running. It's easy to implement this technology, reduced applied cost, and faster time to market. Thank you.
All right, fantastic. Thank you very much. Now the Danfoss team will answer questions from the audience. Please type your questions for the presenter in the Ask a Question box on your screen, and we'll get to as many questions as time allows. Please type the presenter's name before the question if you want to direct it to a particular person. Questions that we do not get to today will be posted online at www.csemag.com. Remember to download a certificate of completion or a copy of today's presentation. Please use the Event Resources tab on the left side of your screen. All right, gentlemen, let's take some questions here. Drew, we're going to start this off with you. Drew, what are some HVAC strategies to reduce carbon emissions in a COVID-19 scenario? This is very topical, kind of an interesting question.
Yeah, thank you, Amara. You know, the jury is still out on both the impact of HVAC systems to the potential spread of COVID, as well as the associated potential solutions to address them. A key topic which has come up, and I just saw an article on yesterday, was the potential of recirculated air to drive potential recirculation of COVID itself, and therefore increase the potential rate of infections. So what I anticipate, or what we anticipate, is going to be a trend associated with that is two things. The demand, and I also heard the governor of New York speak about this, but the demand for higher quality filtration associated with HVAC systems that do incorporate recirculation, and also a move to more systems which don't drive recirculation, such as more of the separation of sensible and latent cooling systems, which with more of the passive cooling on the sensible cooling side. So dedicated outdoor air system with passive sensible cooling on the demand side. I think we'll see more, potentially see more of that in the future. But again, the jury's still out on that.
Yeah, very topical. Thank you. All right, next question. John, this one's directed to you. Can we use codes to reduce greenhouse gas emission impacts from existing buildings?
Yeah, thanks, Amara. Really interesting question. Progressive energy codes, we've seen these in places like Seattle, and yeah, in new commercial and new construction, they are driving very efficient buildings, but they can have the opposite impact on existing buildings, because if you have a building that does need significant upgrades to its HVAC system, but the codes are mandating very efficient systems, that can be very costly. And so it actually has an incentive, it incentivizes the building owner to delay that work. So we have seen kind of progressive codes disincentivize deep energy retrofits. And so I think that's why, in some, like we talked about in some of these places like New York and Washington, they've gone to policies that put penalties in places for not doing these retrofits. So it's a new way of trying to incentivize these retrofits that we really have not had much of an impact on with codes.
All right, thank you. Got it. Ken, we've got a question for you here. Is VFD technology already available in residential HVAC equipment? And if so, is the acceptance rate good, and is it driven by cost, or what are the drivers here, Ken?
I'll answer what I know about the residential. I'm primarily more focused on the commercial side, but yes, it is available in the residential. There are variable speeds that may provide a better air conditioning experience, if you will. Your options for new equipment, it's a key thing on anything with variable speed, it's cost. You just have to decide if it's within your budget to afford the variable speed. So yes, it's available. Yes, there is a cost. As far as wide acceptance, I haven't seen as much wide acceptance in North America as we've seen in other countries, but yes, it is available.
All right, good to know. Thank you. Drew, this question goes back to something that you mentioned. It needs a little bit more clarification. What is a peaking plant? Can you please describe that?
Yeah, absolutely. And it's highly related also to an HVAC solution that we were advocating for this. So when you get to peak rates and peak usage in a utility, what happens is they go from the base load plants to the peaking plants. So base load plants is the nuclear or higher capital cost power generation that they start out with, that the utility always uses as a base load. A peaking plant is generally a natural gas plant today, but it also can come in the form of a thermal storage system or an electrical storage system on the utility side as well. But it's basically, the point is, when you have those hottest days and the highest electrical demand, you need to create that supply side flexibility in the power generation to meet the demand. And you can do that on the supply side or the demand side, either with a peaking plant, which utilities don't like because they're generally very high cost to start and operate relative to other solutions, or energy storage, which is more the trend in the industry. And the energy storage can be either on the supply or the utility side or on the demand side. And it can take either the form of batteries that I talked about or thermal energy storage, both at the utility side as well as the demand side or the customer side.
Okay, okay, very good. Thank you. Let's see, John, this question goes to you. It's actually a two-parter, so let me ask you the first one. First one's first. Are there any peculiarities for the Canadian market or Quebec in particular with its preferential and low hydroelectric rates?
So we do know that Canada has, and specifically Quebec has, and Ontario also in the Toronto area have low electric rates due to the prevalence of hydroelectricity. But I do know that for instance, in the Toronto market, there is aging infrastructure. And so there is really, especially coming from the utility side, many incentives available to increase energy efficiency to delay or offset some of those infrastructure upgrades. So there are a lot of programs coming from Toronto Hydro, for example, to incentivize the installation of variable frequency drives and other energy efficiency measures to help the grid deal with demand, even though there is an abundance of hydroelectric production that keeps energy prices low. So an interesting scenario there.
Okay, good. And John, I'm going to direct this follow-up question to you, but Drew and Ken, you may also have some feedback on this. John, do you have a calculator for your products for carbon reduction or improvement? Is there anything that you can provide there as a resource?
Drew and Ken can help me on the product side, but generally there's still standard calculations emerging for carbon reduction relating to some of these energy efficiency measures. And so we may see different standards and different formulas used in different places. So just a blanket calculator may be difficult, but I'll ask Ken and Drew if we have anything specific to our products that customers can use.
Ken, we have the life cycle cost analysis tool with Oil-Free Solutions or with the Turbocor based offering that and our OEM customers, and Ken can speak to this better than I, but our OEM customers generally have their own tools as well. But from the Danfoss side, we have a life cycle cost analysis tool, which will provide both the operating cost as well as the CO2 emissions reduction potential.
Thanks, Drew.
All right, thanks for that info. Let's get to the next question here. Drew, this one's for you. Can you talk a little bit more about microgrids, and can you provide examples or best practices?
Yeah, absolutely. I'm from the HVAC side, so I'm not an expert on microgrids, but I guess I should be because I speak to them a lot. But the microgrid is basically as opposed to the macro utility grid, and it's driven by, so as you integrate in renewables into the grid, whether it's a micro or macro grid, you have the opportunity to create microgrids based on the on-site power generation. And critical facilities have had this for a number of years as well. Effectively, a data center is a microgrid. And when it's operating on its on-site power. But the idea, whether you're talking about, and I also talked about microthermal grids, as well as macrothermal grids with district energy systems. But the idea with the concept, whether it's thermal or electrical, is to localize the generation and as well as the usage. And so a microgrid is localizing the generation. So on-site power generation with solar and with or with wind, or with a reciprocating engine power generation. That's effectively a microgrid, depending on its tie to the central utility as well. I kind of went around and about, but does that answer the question?
Yes, I believe it does. Thank you.
Okay.
Ken, this next one goes to you. What specific factors contribute to reduced compressor or chiller performance over time?
Interesting question. So the key things that affect a compressor over time is oil contamination, or if you will, oil degradation. So you see in an oil-based system, one of the key factors is you see that the oil will foul either the tubes inside the evaporator or the condenser in fact, or in the compressor. It causes a wear of the mechanical foamant. So as over time, you could see a loss of both efficiency and capacity over time. Whereas in what we claim in our oil-free Turbocor compressors, by having no oil, there's less friction. In fact, it's less than 0.2% friction. Therefore, there's no mechanical wear. So therefore, there is no degradation of performance because you have no mechanical wear internal to the compressor, since we're using magnetic bearings.
Okay, got it. Let's switch gears here a little bit. John, this next question is for you. This is a pretty broad question. What codes are cities adopting to enforce their city carbon policy? Can you give us a few examples, please?
Sure. So usually the first step before these cities have carbon policies like we talked about in New York and Washington, D.C., where there are actually financial penalties for noncompliance, the first step before that is a benchmarking law. And we see this in a lot of cities in Philadelphia, in a precursor in New York, and in Washington, and Seattle, and Chicago. For instance, New York's law, Local Law 84, and amended it, which was passed in 2009 and updated in 2016, requires all building owners that meet a certain criteria, so say over 25,000 square feet, and in certain sectors, require that they report their energy usage into a database. So those are usually the mechanisms that are in place before these emissions laws go into place, so that there is some sort of reporting, and there's a penalty for non-compliance in reporting, and then the cities can then use that database to enforce the emissions laws if and when they are passed.
Okay. Yeah, thanks. That's a pretty broad question, so thank you for taking that one. Okay, Ken, this question goes to you. This is very specific. Is there any intent for Danfoss to implement R290 in the line of scrolls and Turbocor compressors?
Actually, no. We've looked at those different refrigerants, and we do not plan to bring R290 into those compressors. We do have those in our variable speed, small, we call our light commercial applications for reciprocating refrigerant compressors, but we do not offer the Turbocor compressor and R290. We've looked at those natural refrigerants, but of course we feel that that's not something based upon the refrigerant properties that works well with the oil-free compressor.
All
so
right.
I guess the key thing is this, looking at that, we just don't think that's an appropriate application for us.
Okay, good to know. We do have time for one last question here. Drew, I'm going to direct it to you. However, feel free to jump in. John, Ken. This last question is, have there been any studies on the payback period for installing variable frequency drives when considering their negative effects on power factor, which may require capacitor banks to remedy? Any feedback on that?
I think for the specific solutions Danfoss has for that, I think Ken's probably the best to speak to it. But yeah,
sure.
I can touch on it first. So just from our standpoint, what we generally see is that oil-free Turbocor-based systems are in general going to provide a less than 3, in some cases up to around 5-year payback versus the alternative technologies that you could utilize. if you incorporate in the long-term performance and the maintenance of that over time, it'll bring it even shorter than that, less than 3 years. So in general, we see that our technology is coming down in cost in addition to other variable speed technology that's out there. The Danfoss drives applied in scrolls, as well as the Turbocor compressors, but incorporating the performance over time and the ability to maintain that becomes critical as well, and also improves that payback in general to a less than 3-year period. Oh, and also on the power factor, sorry. Yeah, in general, what you see is with incorporating variable speed drives, you do have to address the power quality issues that can potentially drive, and those are becoming better known as variable speed drives do become more ubiquitous. There's both passive and active solutions to those. In general, what we see is that active solutions for the larger applications do tend to be the best solutions for those, but can address that power factor issue to bring it up to the 99 to 100% level, and eliminate the issue at the same time as also allowing scalability with the active solutions to apply it on multiple units or multiple compressors on a single unit.
All right, got it. Well, thank you for those great questions. And thanks again to our speakers, Drew Turner, John Sheff, and Ken Koehler, for sharing their time and expertise. And I'd like to extend a special thank you to our sponsor, Danfoss, for sponsoring today's event. Now that we are just about done, we want to hear how we did. An exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it because we use this information to improve future webcasts. Finally, on behalf of Consulting Specifying Engineer and CFE Media and Technology, I'd like to thank you for attending. This now concludes today's webcast. Thank you and goodbye.